In the previous lecture, we have learned the definition of a sample RTT, but the sample RTT is already happened. So in order to know the next round trip time, so we need to estimate the next round trip time. So how can we get the estimated round trip time? Actually, it's based on this equation. This sample RTT is the previous one round trip time we already get from the history. And this one, this estimated round trip time, is the previous estimated RTT we already get from the previous result. And also we will give a different weight to each element. In this equation, we will give alpha to the sample RTT and give 1 minus alpha to the previous estimated RTT. So, and then in order for us to better understand this equation, so let's see this figure. This figure, the x-axis is a timeline along this direction, and for the y-axis is the round trip time. And for this, the last sample, we use the blue diamond to represent the sample RTT, and we use the pink square to represent the estimated RTT. So for this sample RTT, which is the last one, and the estimated RTT, which is the previous pink square, which is last one, this one. And also this estimated RTT, the previous estimated RTT, is based on the entire history. Therefore, for this equation, we call it exponential weighted moving average. And also the influence of the past sample decreased exponentially fast, which to represent this term. Because we want to give higher weight to the previous sample RTT. And usually or typically the value of alpha given is a point 1 to 5. Our final goal is to calculate the timeout interval. In the previous slides, we already know that the timeout interval should be a little bit longer than the round trip time. And since we already know the estimated round trip time, so in order to calculate the timeout interval, we need to use the estimated round trip time plus a safety margin. And the larger variation in estimated round trip time will lead to a larger safety margin. And also the larger safety margin can be treated as a deviation between the sample round trip time and the estimated round trip time. So how to calculate this deviation? We just simply use the sample round trip time minus estimated round trip time. But sometimes this result should be a negative and sometimes maybe positive. In order to get a real value or the positive value for this result, we just use a absolute value to get it. And also to calculate the estimated deviation round trip time, we use the same trick, which is the exponential weighted moving average, which based on the previous deviation round trip time, which is this one. And also the historical or previous estimated deviation round trip time is this one. Still, we gave a different weight to each term. And for the previous estimated deviation round trip time, we gave it 1 minus beta. And for the current deviation round trip time, we give a beta. And typically, we give the beta value as a 0.25. Then finally, we can calculate the result of a timeout interval, which is estimated round trip time plus 4 times of estimated deviation round trip time. So probably you will ask why the value is 4 instead of others. But this question is already out of the domain of this class. So we are not going to do the mathematical analysis for this equation. If you are really interested in how they get this number 4 instead of others, you can search it online by yourself, and probably you will dig out the real answer which can satisfy your questions. Then let's see how the TCP protocol implement reliable data transfer. Here, the TCP protocol will create a reliable data transfer service, which is on the top of the network layer, which is can only provide us an unreliable service. And also, we have learned the TCP protocol is using pipeline segments in order to improve the link utilization. And also, the TCP protocol will use a cumulative X on the receiver side. Then the TCP protocol will use a single retransmission timer. So based on the description of these 3 features, the TCP protocol is very similar as the go back N solution. Then let's see the retransmission. The retransmission can be triggered by 2 conditions. The first one is based on the timeout event. Another condition is based on the duplicate X. So these 2 conditions, which one gets satisfied can trigger retransmission. Then let's consider a simplified TCP sender. But here we ignore the duplicate X, and also we ignore the flow control and congestion control in order to simplify the description of this TCP protocol or TCP sender side. Then let's see the TCP sender events. The data received from the upper layer, which is the application layer, it will create a segment with the sequence number. And also we have learned in the previous slides, the sequence number is a byte stream number of the first data byte in segment. Then it will start a timer if this segment is the first segment in the window. Think of the timer as for oldest unacted segment. So still here, the timer is exactly the same as the timer we used in go back N solution. The timer is to start from the oldest unacted segment. For the expiration interval, which is based on the timeout interval. And in the previous slides, we already know how to calculate this timeout interval. So when the timeout happened, it just retransmit a segment that caused the timeout. Here, there's one thing I want to point out is segment instead of segments. So that means when the timeout happened, the sender only retransmit a single segment, which is caused the timeout, and then restart the timer again. When the ACK received, if the ACK acknowledges previously unacted segments, then update the window position, start the timer if there are still unactive segments. Then let's see this TCP sender side. This is a finite state machine. Still, we only consider for this sender side, we only have one state, which is a wait for event. So initially, the sender side will do initial setting, which is for initialize the connection between the two sides, the sender and the receiver. For the next sequence number and the send base, two pointers, both of them will be set up as the initial sequence number. They are the same, which is randomly generated. We already talked about in the previous lecture. And then when the data received from the application layer, it just create a segment based on this next sequence number, and then pass this segment to network layer. And also don't forget to update our next sequence number by the length of the data. And then do a checking to see if the timer currently running or not. If the current timer is not running, means this segment is the first segment in the window, so we need to start the timer. So when the timeout happened, we only retransmit the not yet act segment, the single segment, which with the smallest sequence number, and then don't forget to start the timer again. When the ACK received with ACK field value Y, and then we will do a checking to see if the Y is greater than send base. If this condition is true, so that means this Y is in the window. Then we need to update this Y. We need to update our send base to Y. After that, we need to further checking to see if there are currently not yet active segments. If still have some active segment on the window, we need to start the timer again. Otherwise, we just stop the timer. Then let's see the TCP retransmission scenario. Here we have multiple retransmission scenarios. The first one is lost ACK scenario. So the host A send out a segment with the sequence number 92 and combined with 8 bytes of data to host B. Then after host B received this segment successfully, then host B will send acknowledgement for the segment 92, which is the next expected sequence number 100 back to the host A. However, unfortunately, this ACK acknowledgement control message get lost. After the timeout gets triggered, the host A will retransmit this segment 92 to host B and then go back to normal. Another scenario is a premature timeout. For this one, this time the host A continuously send two segments to host B. One is segment 92, another one is 100. However, before the X arrived the host A, the timeout already triggered because they set up the timeout is too short. Then when the timeout happened, the host A will do a retransmission. So as we already talked about for several times, the premature timeout will cause the consequence is to do the retransmission. However, here it doesn't like the retransmission in the go back N solution. all the unacted packets will be retransmitted again from the sender to the receiver. For the TCP retransmission, it only retransmit the segment which caused the timeout, only retransmit a single segment to the receiver side, which is different from the go backend solution. The third scenario is a cumulative ACK. For this one, still host A will continuously to transmit two segments which are 92 and 100 to host B. So even though the ACK 100 lost, as long as host A receive ACK 120, the host A can guarantee that host B is already received segment 92 and segment 100 successfully, because the TCP protocol will use a cumulative ACK. So that's the beauty of cumulative ACKs. Then let's see the TCP ACK generations, and for this details is already written in the RFC 1122 and the RFC 2581 files. So you can check the details from these two RFC files. Then here we have 4 pairs of event and actions. So let's learn them one by one. First, let's see the first pair. The event is arrival of in order segment with the expected sequence number. All data up to expected sequence number already act. For this event, it will trigger an action is a delayed ACK. Wait up to 500 milliseconds for next segment. If no next segment, send ACK. So for this event and action pair, I'm going to use an example to further explain it to you guys. However, here I prefer to use a segment number as the sequence number instead of use the first byte of the segment as the sequence number, because the segment number is easier for us to understand. Okay, then for this event and action pairs, suppose on the receiver side, packet 1 and packet 2 has been received successfully, and also the ACK already sent it back to the sender side. Then packet 3 or segment 3 received by the receiver. Then under this kind of a situation, the TCP receiver will delay the ACK and wait to 500 milliseconds for to send the ACK3 back to the sender side. If after 500 milliseconds the receiver still doesn't receive any in order segments, it just transmit ACK3 back to the sender. So this is the first event and action pair. So let's see the second pair. Arrival of in order segment with expected sequence number. One other segment has ACK pending, and then the action is immediately send a single cumulative ACK, acting both in order segments. So the example for this one is still segment 1 and 2 has been received successfully, and also the ACK for them is already sent it back to the sender side. And also segment 3 is already under the pending situation. So this one is pending, which means segment 3 is already received by the receiver, but not sent the ACK yet. Then packet 4 or segment 4 has been received. Then the receiver will immediately send ACK4, send ACK4 back to sender side to notice the sender, okay, packet 3 or segment 3 and segment 4 has been received by the receiver side successfully. And for the third pair, event and actions is arrival of out of order segment higher than expected sequence number gap detected, and immediately send the duplicate ACK indicating sequence number of next expected byte. So for this one is still packet segment 1 received an ACK, segment 2 received an ACK, then segment 4 received, which is out of order. Under this kind of a situation, the receiver will automatically or immediately send ACK2 back to the sender side because packet 4 is out of order. So immediately send the highest in order segment number, which is ACK2 back to the sender side. Then let's see the last pair, event and action. Arrival of a segment that partially or completely fills gap. Then action is immediate send ACK, provided that segment starts at a lower end of a gap. Then example is still segment 1 received an ACK, segment 2 received an ACK, segment 4 received, and the duplicate ACK is already sent back. Then after that, segment 3 has been received. Under this kind of a situation, the receiver will send ACK4 back to the sender side. Another scenario is still segment 1 received an ACK, segment 2 received an ACK, segment 5 received, and the duplicate ACK2 has been sent back for this out of order segment. Then segment 3 has been received. Under this kind of a situation, the receiver will immediately send ACK3 back to the sender side. Next, let's see the TCP fast retransmit. So in the previous slides, we already mentioned the TCP there are two conditions can trigger TCP retransmit. One is timeout, another one is duplicate X. But usually the timeout period is relatively long. So if we waiting for the timer get times out before resending the lost packet, usually we will experience a longer delay. However, the second condition, which is a duplicate X, which can detect the packet loss through a fast way. Here is the sender often sends many segments back to back. If a segment is lost, there will most likely be a many duplicate X. Then the rule for TCP fast retransmission is if a sender receives 3x for the same data, and also we call it triple duplicate X, then the sender will retransmit the unacted segment with the smallest sequence number because it's very likely the unacted segment just get lost on the way. So it's not necessary to wait for the entire timeout to be triggered. Then let's see an example for this TCP fast retransmit. So we have two hosts, host A and host B. Both of them, they are set up TCP connections. And the host A will continuously to send a set of segments to the host B. The first segment with the sequence number 92 is arrived at host B successfully. However, the second segment with the sequence number 100 get lost. Then after that, all the segments, this one, and this one, all of them becomes out of order segments. Therefore, when host B receives this out of order segments, the host B will not retransmit, will transmit the duplicate X, which is X 100, X 100 to the host A to notice the host A. There is the host 100, the segment 100 is already lost. Then, after the host A receives these 3 duplicates, then the host A can immediately trigger a retransmission for this segment 100 to host B. And also here we need to do a counting. So 3 duplicates ACK plus the original ACK. In total, the sender host A will receive 4 ACK 100. Will receive 4 times. Then let's see this TCP flow control. First, let's understand this figure. Above this line is the application layer, which is managed by the users or the developers. And below this line is transport layer, network layer, link layer, and the physical layer, which is maintained by the operating system. So between the application layer and the transport layer, there is a buffer. We call it TCP socket receiver buffer. However, this buffer is different from the buffer we already talked about several times in the previous slides. For that buffer, when the receiver receives out of order segments, it will temporarily stored on that buffer. We can call it out of order buffer. However, for this TCP socket receiver buffers, and all the segments stored on this TCP socket receiver buffers, they are in order. So the purpose for using this TCP socket receiver buffers is because the application processing speed to retrieve the segments from this buffer from the transport layer may be slower than the in-order segments arriving speed. Therefore, the difference of the segments will be temporarily stored on this TCP socket receiver buffers. And then let's see how it works. So suppose there's new segments around this device. It will first through the network layer and then deliver to the transport layer. And the transport layer will do a checking to see if this segment is in order or not. If in order, it will be delivered to this TCP socket receiver buffers directly. Otherwise, if it is out of order, will temporarily stored on this out of order buffer. And when the in order segment arrive on this transport layer, it may change this out of order segments becomes in order. Therefore, they can deliver this segments just change to in order and to this TCP socket receiver buffers. And the purpose for using the flow control or design the flow control is to give the ability for the receiver to control the sender. So the sender will not overflow the receiver buffers by transmitting too much or too fast. Then let's see the details of flow control. The receiver will advertise a free buffer space, which is this part. Is a RWND value in TCP header of a receiver to sender segments. And also here has a definition, which is a receiver buffer. The size of this receiver buffer will be set through the socket options. Usually, the size of this receiver buffer will be set as 4096 bytes by default. And many operating systems, they can auto adjust the size of this receiver buffer. And the entire buffer, we call it receiver buffer. Therefore, the sender can, when the sender receives this RWND value, and based on this value, it can adjust the sender window size to limit the amount of unacted data to receiver side in order to guarantee the receiver buffer will not be overloaded. Let's continue to see the connection management. So before exchanging data, the sender and the receiver side, they need to initialize the or set up the connection between each other. We also call it handshake. And both sides will agree to establish connections, and each side will know the other side willing to establish the connections. And also both sides they need to agree on connection parameters. So, for example, here, each side, no matter the client side or the server side, they need to set the connection state as ESTAB, which is shorted for establish for each side. And also the connection variables, each side will randomly generate a sequence number used for later to exchange the data between the sender and the receiver. And also each side will set the receiver buffer size because no matter the sender side, no matter the client side or the server side, they need to receive the data from the other side. And also each side will prepare a socket in order to establish the TCP connection for later on. Then let's see this TCP three-way handshake. So both the client and the server side, they are start with the listen state, and then the client side will start or initial the communication to the server side, which is to randomly generate a sequence number as X and send this TCP SYN message to the server side. And also, do you remember when we talk about the TCP segment format? In the header part, there is a SYN field. So for this information, it will set the SYN bit by 1 and also with this sequence number X and send to the server state, to the server side. And then the client state will change to SYN send state. On the server side, when the server receives this message or this segment, it will randomly generate a sequence number, which is Y, and also send a TCP SYN ACK message, which are ACKing this message, and send this ACKing message, which is this one, back to the client side. And also this message will set the SYN bit to 1 with the sequence number Y, and also it will set the ACK field by 1, and this ACK number will be this sequence number plus 1, which is the next sequence number from the client side. And then the server state will change to SYN received state. Then the client side receive this SYN ACK message, which indicate the server is alive. Then it will send the ACK for this message. And also for this ACK message, we'll combine with the client to server data. For example, if there's a client will request a web page from the server side, and in within this ACK message, it very possible will combine with the URL of this server's website. And then the client state will change to ESTAB, which is establishment. For the server side, after the server receives this ACK message, it will indicate the client side is alive. Then the server side, the same as the client side, will change to establishment state. Then we know how to initialize or do the handshake, and also we need to know how the TCP connect protocol closing a connection. The client and the server each close their side of a connection and send the TCP segment with the FIN bit or set FIN bit to 1 and respond to receiver received FIN with ACK. On receiving FIN ACK can be combined with own FIN. Simultaneous FIN exchanges can be handled. And then let's see how it works. So since the client and the server, they want to closing a connection, so that means they are already connected with each other. Therefore, their starting state is both of them are established state. Then the client side will call this close function and then send a segment to the server side, which within the segment, it will set the FIN bit to 1, and the sequence number is X. After the client send this segment out, it can no longer send, but it can receive data. And also the client state will change to FIN wait 1 state. On the server side, when it receives this segment, the state of a server side will change to close wait state, and then the server will send an ACK acknowledgement for this segment, and also set the ACK bit to 1, and the ACK number is this sequence number plus 1. Send this segment to the client side. When the client side receives this segment, it will set the client state to FIN wait 2 state, which wait for the server close. And after the server state changed to close wait, it can still send data. And then after a moment, which is a couple of milliseconds, the server side will send another segment which set the segment FIN bit to 1 combined with the sequence number Y, send it back to the client side. But after the server send this segment out, it can no longer send data, and also the server state will change to last ACK state. So for the client side, after the client receives this message, this segment, the state of a client side will change to time the wait, and then immediately it will send an ACK acknowledgement back to the server side, which is an ACK to the previous segment sent it from the server side. And also, the client side will wait for 2 times maximum segment lifetime because the client side will make sure this segment can be received by the server side without any problem. If there's a problem, there will be a message. We'll send it from server side, go back to the client side, and the client side will capture it. And then after the client side wait for 2 times of maximum segment lifetime, the client side will change to closed state. And for the server side, after the server received this acknowledgement from the client side, it also will change the server state to closed. After both client and the server, they change the state to closed state. So that means this TCP connection has been closed without any problem. So far we have finished congestion-oriented transport for the TCP protocol. And then let's continue to talk about the principles of congestion control. So what the reason can cause the congestion is because too many devices they sending too much data and also sending too fast. Therefore, the network is hardly to handle this much of data transfer, which is different from the flow control. As we already mentioned, the flow control is happened on the end devices. However, the congestion control or congestion is happened on the router, which belongs to the network core part. And also the consequence of congestion, it can cause the packet loss because when the router's buffer get filled up, if there's a newly arrived packets, the router will simply drop it off because there's no buffer can handle it, which can cause the packet loss. Another one is if the buffer on the router, most of the part or most of the portion is already occupied by some packets. So for the newly arrived packets arrive this router, it must experience a longer delay due to the queuing delay. So the two consequences is one is packet loss, another one is a longer delay. So for this congestion problem, it's a top 10 problem in computer networking area. Then let's see the costs and reasons for the congestions. First, let's see the scenario one. Suppose we have two senders, which is host A and host B, and also we have two receivers, which are two servers, and we have a single router in the middle with infinite buffers. So that means this router can never drop off packets. And also output link capacity is R, which is here. And also we consider or the assumption is there's no retransmissions. Therefore, the maximum per connection throughput will be R divided by 2 because each user or each host will occupy R divided by 2 of the output link capacity. Then let's see the average delay. I'm not sure if you guys still remember when we talk about the queuing delay, there is a very important definition, which is the traffic intensity. So which means if the traffic intensity are close or equal to 1, the average delay will be goes to infinity. Actually here, the same problem will be happen if this router fully occupied by host A and host B. So that means the traffic intensity will be equal to 1. Therefore, the average delay will be goes to infinity. And then let's see the scenario 2. Here we still suppose there is only one router in the middle. However, for this version, we suppose the buffer of the router is limited, and the sender retransmission of timeout packet. Then, from the application's wheel, the application layer input and the application layer output should be equal, because whatever stuff sent from the application input will be received by the application output or by the receiver. However, on the transport layer, the input may include retransmissions, just like we show here, the lambda in prime, which is the original data plus the retransmitted data, which is greater than or equal to lambda in, which is the original data. So here, suppose the sender has a perfect knowledge or information from the routers. So that means the sender sends only when router buffers available. It should be like this. If that's the case, the output is still R divided by 2. However, if we suppose the sender only known the packet loss, so the packets can be lost, dropped by the router due to a full buffers, and then the sender only retransmit if a packet known to be lost. Then let's see this one. So for this version, we can see the sender will issue a retransmission when the router's buffer get fills up. So when sending at R divided by 2, some packets are retransmitted, but asymptotic good put is still R divided by 2 if we from the long-term view. So the throughput is still close or equal to R divided by 2. But the realistic is there may have some duplications for the packets will be received by the receiver. Especially when the timeout happened. So that means the receiver will receive 2 copies of the same data. So if that's the case, we can see that the throughput can never reach to R divided by 2 because some duplicated information or duplicated data will be received by the receiver. Then the cost of the congestion is more work will be done or more retransmission will be done for given a good put. Another cost is unneeded retransmission will be triggered, which can decreasing the good put. Then let's see the scenario 3. So here we suppose have 4 senders, which is host A, B, C, and D. And these senders, they will use a multiple hop path to transfer the data over the internet. And also under this scenario, there are timeout maybe happen, which can trigger a retransmission. So here, let's see a question. What happens as the lambda in, which is the original data, and the lambda in prime, which is the original data plus the retransmitted data increased? Then let's see the result. So as the red lambda in prime, which is the input from host A, get increase. So all arriving blue packets at upper queue are dropped. Blue throughput will be equal to 0. So what that mean? It means this router, suppose this router is fully occupied by host A because host A increased its input speed, which is a lambda in prime. Then when the host D arrive this router, on the router's buffer there's no any free space. So that means all the host B packets will be dropped by this router. So that means the blue or host D throughput will become to 0 because the packets of a host D can never reach its destination, which is a host B. Then there's another cost for the congestion, which is when the packet dropped, any upstream transmission capacity used for that packet was wasted. So when you increase your input speed for some points, you should stop it. Otherwise, you will decrease the overall throughput of the entire network. And then let's see, so we already detected the congestion problem. So how we can address this congestion on the internet, or what's the approaches we can use to do the congestion control? Generally, we have two solutions. One is we call it end-to-end congestion control. For this one, there's no explicit feedback from the network, so the congestion is inferred from end system through observing the packet loss or packet delay. Actually, the TCP protocol will use this end-to-end congestion control solution. So what's the advantage for this solution is it will not bring too much overhead to the internet to the network core part. It will not bring the overhead to routers. That's the advantage for this solution. However, the end systems must handle this problem because they need to infer the congestions based on the packet loss and the packet delay. However, on the other side, another solution is the network assisted congestion control. So for this one, the routers will provide feedback to end systems. So that means you can see there's a involving work for the routers. And a single bit indicating congestions. Here list a numbers of protocols which will use this network assisted congestion control. And also for this version, they will explicit the rate for the sender to send at. So the routers will help the senders to know how much speed you can send the packets out. Then let's learn the last part of chapter 3, which is TCP congestion control. So for the TCP congestion control, the solution we use, which is shorted for AIMD, is shorted for additive increase and multiplicative decrease, which is these two terms. And the approach we use for TCP congestion control is the sender increases transmission rate, which is the window size. Actually, we try to fully utilize the link capacity or the bandwidth until the packet loss occurs, and then we need to do some actions. Later I will show you guys. So when the packet loss happened, so what the TCP congestion control will react. For the additive increase, it just increased the CWND. This one is a congestion window on the sender side. So it just increased the CWND by 1 MSS. The MSS, which is shorted for the maximum segment size. So later, after this slides, I just use MSS, so you guys will know it means the maximum segment size. And for every round trip time until the packet loss is detected. However, for the multiplicative decrease, is when the packet loss detected, this CWND will be cut into half of the size. And then let's see the behavior of AIMD. At the very beginning, it will increase linearly until a packet loss is detected. It will cut the window size by half. Here is half of the window size, and then increase linearly. Another packet loss detected. It also will the window size will be cut into half. Then continuously to do this kind of a behavior. So based on this figure, it shows us the AIMD is just like a saw teeth. Then let's see the more details about the TCP congestion control. So I think this figure you guys are already familiar. For this color, it's a green color to represent the packet already sent it out and act by the receiver side. And after this part, there's purple bars to represent the packet slot cannot be used. And between these two, this area is the congestion window, and we use the yellow color to represent the packet already sent it out but not yet act, which is in flight on the way. For this blue bars to represent the usable pack segment slot. Then the sender limits transmission based on this yin equation, this one, which is the last byte sent, which is this location, minus the last byte act, which is here. So the difference between these two point, which means the packet already sent it out, but not yet act. So for this amount should be less than or equal to this congestion window. However, actually there's another factor all parameters can affect this these values, which is the R, W, and D. I'm not sure if you guys still remember it. And this is the window size on the receiver side. So actually, in reality, this range is decided by the minimum values of these two. But here, since we're talking about the congestion control, so we only care about this value. But in reality, we need to consider both of them and take the smaller one. And also here show us the congestion window is dynamic, and it is a function of a perceived network congestion. And also here the TCP sending rate is based on we send this much of bytes and we wait a round trip time for the X, and then we send more bytes. So in order to calculate the TCP sending rate, it's just based on this result. We use the congestion window divided by the round trip time. We will get the roughly rate or the roughly TCP sending rate. Then let's see this TCP slow start. Even though the name of this this part we call it the TCP slow start, but actually the speed is not slow. And then let's see. So when the connection begins, increase the rate exponentially until first loss event happened. So initially we will set the congestion window as 1 MSS, and then we double the congestion window every round trip time when we receive the new ACK. So here, done by incrementing CWND for every ACK received. Then let's see the right side figure. So the host A send the first segment to host B, and then host B send an ACK back to host A side. So when host A receives this ACK, it will increase the congestion window by 1. So initially it's just 1 MSS. And when the host A receives a new ACK, it will increase the window by 1. So that means currently for this point, the congestion window is 2 MSS. And then from this point, receive a new ACK, it will become 2 MSS. And for this one, it will become 4 MSS. Therefore, we can see the pattern. So for every round trip time or every round, the congestion window will be doubled. Initially it's 1, and then it's 2, 4, and after that should be 8, 16, and 32. So you guys will know the pattern for the slow start. Therefore, the summary here shows us initial rate is slow, but the increased speed is exponentially fast because each time will double the previous size. And then let's see when the packet loss happened, how to detecting the packet loss and reacting the packet loss. Here the TCP congestion control, actually we have two versions. The first version we have is TCP, we call it TCP Reno. Another type, we call it TCP Tahoe. The first, let's remember we have two types. And then the packet loss will trigger a retransmission. And also in the previous slides, we already talked about that. There's two conditions can trigger the retransmission or can detect the packet loss. One is timeout. Another one is duplicate X. So first, let's see when the packet loss uh, is detected by the timeout. The congestion window will be set to 1 MSS, and then the window then grows exponentially to a threshold, then grows linearly. Do you remember in the previous slides we have learned a slow start? It will increase exponentially until it reach the threshold. So we have a threshold. So later I will tell you guys so how to set the threshold and how we can use the threshold. And after the congestion window reach the threshold, it will grow linearly. For another situation, if the packet loss is detected by 3 duplicate X, and also if we consider a TCP Reno version, then the duplicate X indicate the network is capable of delivering some segments because the sender can still receive these 3 duplicate X. So that means the internet is not fully congested. It can still transfer some information or some packets because the sender can still receive 3 duplicate X. Then the congestion window will be cut in half window. For example, before the packet loss happened, the window size is 10. However, if the packet loss is detected by 3 duplicate X, then half of the congestion window will be 5, and also plus 3 then grows linearly. Therefore, the congestion window will be set as half, which is a 5, plus 3, which is equal to 8. And after this 8, after the congestion window set it as 8, and then start from 8 to grows linearly, and each time it just increased by 1. For the TCP Tahoe, this type, no matter the packet loss is triggered by or detected by the timeout or detected by the 3 duplicate X, it always sets the congestion window to 1 MSS. So later we have a writing assignment, which is a writing assignment 3. We will have a question to ask you guys to figure out this type or this detecting and reacting to packet loss problems. And also you guys need to be careful. So what type of a TCP congestion control you ask to answer the question because they are different. So let's point out the main points. So if you using TCP Tahoe type, no matter the packet loss, it's triggered by timeout or triggered by 3 duplicate X, the congestion window will always be set to 1 MSS. However, if you use the TCP Reno version and if the packet loss is triggered by timeout, still the congestion window will be set as a 1 MSS. However, if the packet loss is detected by 3 duplicate X, we will use this one. The congestion window is cut in half, window plus 3, then grows linearly. So you guys need to be careful. Here, let's see how to switching from a slow start to CA. And the CA here is shorted for congestion avoidance. So when should the exponential increase switch to linear? So before we talk about the examples on the right side, this figure. So first, let's learn some variables, and or we do some implementations. The variable SS thresh, which is the threshold we already mentioned in the previous slides. And also on the loss event happened, the SS thresh is set to half of the congestion window size. So for this SS thresh set to half is no matter the packet loss triggered by timeout or triggered by 3 duplicates X, and also no matter you use the TCP Tahoe or you use the TCP Reno, all of them under all the situations when the packet loss happened, the SS thresh will be set to half of the previous congestion window size. Then let's see this example. First, we will see the TCP Tahoe version, which is represented by the blue lines. So initially, the congestion window size will set it as 1 MSS, which is this point. And then for next round, it will increase to 2 MSS and then 4 MSS. Or, by the way, initially the SS thresh for this case will be set as 8. Then for the next round, the congestion window size will be increased as 8, which is already reach our SS thresh. So after that, after the congestion window size reach our threshold, it will increase linearly after that. After that, for each round trip time. Then for round 5, it will become 9, and then 10, 11, and 12. So until the congestion window reached to 12, then the packet loss happened. Since right now we are considered for using the TCP Tahoe version, therefore no matter the timeout triggered or 3 duplicates X received, the congestion window size will be set as 1 MSS. And also don't forget, so after this packet loss, after this round, the packet loss got triggered, the SS thresh will be resetted as half of this window size. Because after this window size, after this 12 window size, the packet loss happened. Then the threshold will be changed to half of this 12. That means 12 divided by 2, which is 6. Therefore, after round 8, the threshold will change to 6, which is here. And then start from round 9, the congestion window size will start from 1 and 2 and 4 and then 6 instead of 8 because our access thresh or our threshold is 6. So even though for the next after 4, if we double the size, which is 8, but for the slow start, we cannot go over the threshold. Therefore, after 4, it's just a 6. And the start from 6, it will increase the linearly, which is 7, 8, and 9. However, if we consider to use the TCP Reno version, so start from round 1 all the way to round 8, which is exactly the same as a TCP Tahoe version. But after round 8, which is the window size already reached 12, which is here, when the packet loss happened. And also, we know for this TCP Reno version, which is represented by the black line, the packet loss is triggered by 3 duplicate X because for the round 9, the congestion window size not change back to 1 because it changed to threshold plus 3, which is 9. Therefore, based on this value, we can infer this packet loss for the TCP Reno version is triggered by 3 duplicate X. Then, because this 9 is already higher than the threshold, so it will increase linearly. And then for each run, it just increases the congestion window by 1. Therefore, it's 9, 10, 11, 12, 13, 14, and all the way to 15. Then let's summarize this TCP congestion control. So initially, the TCP sender will start from the slow start state. And before they start sending, so they need to do some initialization settings, which is here. They will set the congestion window as a 1 MSS, and also for this case they set the SS thresh as a 64 KB, and also the duplicate ACK count to counting how many duplicate ACKs received by this sender. Initially we just set it as 0. And here has multiple possibilities. The first one, let's see this one. When the duplicate ACK event happened, it just increased the duplicate ACK count increased by 1. If a new ACK received or new ACK event get triggered, and then for each new ACK, the congestion window will be increased by 1 MSS. And also the duplicate count will reset as a 0. However, when the timeout event gets triggered, the SS thresh will set it as half of the congestion window, and also the congestion window will be set as a 1 MSS, and still the duplicate ACK count will reset it as 0. However, as the new ACK keep receiving, when the window size or congestion window is greater or equal to the SS thresh, so the state will be changed to congestion avoidance state. And under this state, we still have multiple possibilities. So first, let's see. Under the congestion avoidance, if the new ACK received, we only increase the congestion window by a smaller portion, or 1 over congestion window size this much. So I'll give you an example. Suppose when the sender already moved to congestion avoidance state, so the sender send out 5 segments to the receiver side, and then for each new ACK received by the sender, the congestion window will increase to 1 over 5. So that means if this file new ACK has been received by the sender, so in total the congestion window will be increased by 1. This is the meaning for this equation. And then the duplicate ACK count will be reset as 0. Another possibility is when the duplicate ACK received, it just increase this counter. And when the timeout happened, still the threshold will change to half of the window size, and set the congestion window as a 1 MSS, and reset the duplicate ACK count as 0, and then don't forget to move the state back to slow start. Another possibility is when the duplicate count equal to 3, so that means under this state, the sender receive 3 duplicate ACKs. Then the threshold will change to half of the congestion window size, and the congestion window will be set as the threshold plus 3, and then move to faster recovery state. Then under this state, if continually or keep receiving duplicate ACKs, so for each time the congestion window will be increased by 1 MSS, because each duplicate ACK received by the sender, so that means the receiver can still receive out of order segment. However, if under the fast recovery state, if there is a new ACK received, then the congestion window will be set as the threshold plus 3, and then set the duplicate ACK count to 0. After that, go back to the congestion avoidance state. Another possible is the timeout event triggered under the fast recovery state. It still do the same thing. We'll change the threshold to congestion window over to half of the congestion window, and set the congestion window as a 1 MSS, and the duplicate ACK account or ACK count set as a 0. And for this one, it's the same. When the state under slow start, when the triple duplicate ACK received, it also can move to faster recovery state and also do this kind of actions. Then let's see this TCP throughput. So the average TCP throughput can be treated as a function of window size and round trip time. So here we ignore the slow start. We are assuming there's always some data can be sent out from sender side. So here the W represent a window size, which is measured in bytes, and when the packet loss occurs. And the average window size is 3/4 window size. So later I will tell you guys how to do the calculation or how to get this 3/4 window size. And the average throughput should be the same value, which is 3/4 window size divided by the round trip time. So how to get the average window size? As we know, so if there's no packet loss happened, so the window size should be W or 1W, right? When the packet loss happened, we will change the window size to half, which is 1/2 window size. If we want to get the average, we will use these two values, divide by 2, right? And then we can get 3/4 window size, which is this one. Therefore, the average TCP throughput should be 3/4 window size divided by the round trip time, and with this much of bytes per second. And then I see the TCP fairness. The fairness goal is for different TCP connections if they using the same link or if they share the same link, the bandwidth will be fairly distributed for each connection, TCP connections. So which means if we have k TCP connections and the bandwidth of the link is R, and for each TCP connections, the bandwidth can be used as equal to R divided by K. So that's the TCP fairness.